Okay, I hope you guys are doing well and adapting to this new environment. Um, we are through with our second portion of the class. The first part was just primarily an introduction, getting familiar with the nomenclature, the methods, the ideas within the controlled environment. And then the second half, we really started looking at this primary tool, one of the primary tools we use in controls, which is root locus. And so we spent some time looking at root locus and ultimately being able to see the response of the system as we vary the k, and then more importantly being able to reshape that root locus to get desired results by adding poles and zeros to reshape the branches of that and move them where we want it to be. So this is a very popular and common way to start looking at the system. Now, our third portion of the course is a different look at this, um, and I want to caution you a little bit here. If you try to take the root locus stuff into the Bodhi, you're going to get lost. And so, in your mind, kind of back up to before Bodhi, before root locus, and think about the original stuff. That all still applies. We're just going to apply it now in a different way. Rather than looking at the step response and the roots of the equation that give us the response of the system, now we're going to inject frequencies and an S variable into the equation and get the results out. Let me show you here real quickly. Let me pop over to OneNote. What we've done up to this point is we have our characteristic equation, something like S plus 3, our characteristic equation. And what we've been doing is setting that equal to 0 and then solving, and what we end up with then is S is equal to minus 3, which would be a root of our system. And we find all the roots, and the roots then tell us where the system will oscillate naturally, its natural frequencies. And from that, we can determine the response of the system, the transient response of the system. So alternately, another thing that we do with equations, and you remember from math, we can write them, say, like f of s is equal to s plus 3. And then we say for s equals 2. Then we would come in here and solve this for s equal 2, and we would have 2 plus 3, and of course we know that would equal 5. And so what we've done in this case, rather than solving for setting it equal 0 and solving for the roots, we're putting a value into the system and seeing what the response is. It also would be akin to the idea of having some sort of function, say some sort of parabola like this. And we could come in here and we could solve for the roots, which would give us these points of our intersection with our real axis, or we could go in and substitute x for every value and come out with a full graph of this, like is shown here. So two different approaches to the problem, and we're going to be looking at the second. We've done the first case where we look at the roots of the system, and now what we're going to be doing is interjecting a frequency, actually a bunch of frequencies, into the transfer function and seeing what the outcome is. And so this method sprung out of a different application. The the root locus really sprung out of mechanical applications. Mechanicals were looking at a way to describe the response of a system in regard to how a system was going to respond to the transients. If we put an input into our system, move from point A to point B, what is going to happen? How fast is it going to happen? How much oscillation are we going to have? How can we improve that? That was really the thrust of the root locus development. The alternate, which we are going to call the frequency response, and came out of communications. Electronics engineers were working on communications back in the day, and of course what they were interested in is how well a sine wave could be pushed down an environment, either a wire or over air, in the form of radio waves, and then how can the receiver pick up that signal and reproduce, how well would it be able to reproduce that signal, and what kind of fidelity would they get. Of course, Bell Labs was big in this, and the communication and the telephone, pushing an audio signal down a wire and then having it reproduced as audible sound at the other end. And so engineers were working on this, and so they were working with sine waves, and they were interested in how these sine waves of varying frequencies would be reproduced in the application. And so they developed this whole frequency response methodology for looking at the system. So we're going to be looking at that. The primary tool we're going to be using is a tool called a Bode plot. There's a couple of ways to look at this, a Nyquist and Nichols plots, but Bode is by far and away the most popular. And so we're going to use the Bode, and we're going to do the same thing. We're going to figure out how to sketch a Bode plot for a transfer function and figure out what it means, and then figure out how to move it around to get the performance that we want from it. So we're the last portion of this class, frequency response, primarily focused on the development and application of the Bode plot. Okay, so that's intro, and we'll get into it and see where we go.